High-head hydropower relies on raw kinetic force. Water channels down a steep mountain penstock, converting vertical pressure into velocity to spin a heavy steel turbine. Engineering one of these systems starts with rigid site conditions. For this specific project, we need to extract exactly 1,000 kilowatts of grid power from a 400-meter gross head drop. Our turbomachinery constraints dictate a specific speed, or NS, of 14, using a multi-jet configuration with exactly 2 jets. The engineering challenge here lies in translation. We must convert these abstract performance targets into the precise physical dimensions of a cut metal machine. These initial parameters act as the primary constants. Because the specific speed, required power, and available head are locked, the physical dimensions that emerge from the calculation are a direct consequence of these fixed inputs. We begin with a blank slate. To map the physical reality of this undimensioned pelting wheel, we need to solve for 3 primary variables: the outer wheel diameter, the jet diameter, and the rotational speed. We log our starting gross head of 400 meters into our working constraints. Next, we log the target total power output of 1,000 kilowatts. Because this is a 2-jet system, the specific speed constraint requires us to look at the power per jet, meaning we are designing for 500 kilowatts of output from each nozzle. To calculate the final dimensions, we must move systematically through the physics, starting with fluid dynamics to find our water velocities before we can determine the shape of the mechanical runner. Before reaching the turbine house, water loses energy to friction against the penstock walls. We calculate this loss at 5%, subtracting 20 meters from our gross head. That leaves a net head of 380 meters, representing the actual, usable energy arriving at the nozzle. We translate that downward pressure into linear fluid velocity. To account for internal friction at the nozzle tip, we apply a velocity coefficient of 0.98. Applying this coefficient to our 380-meter net head provides our absolute jet velocity. Water exits the nozzle at 84.61 meters per second. To harvest maximum energy, the turbine buckets must maintain an optimal speed ratio, or Q, of 0.46 relative to the water. Multiplying our jet velocity by that 0.46 ratio tells us exactly how fast the physical mile bucket needs to travel, 39.719 meters per second. We have our linear fluid velocity. Now we must pivot the calculation to the rotational dynamics of the wheel assembly. Returning to our specific speed of 14, this parameter defines the relationship between rotational speed, power output, and operational head. We input our known variables, 500 kilowatts per jet and our 380-meter net head. Resolving this isolates our operational rotational speed, 1050.4 RPM. This links our linear bucket speed to our rotational shaft speed. Knowing how fast the bucket moves through space and how many times the wheel turns per minute constrains the physical size of the wheel. The mean diameter equation links these forces. The tangential velocity of the bucket is equal to pi times the mean diameter times the RPM divided by 60. Solving for the mean diameter gives us a value of exactly 0.7721 meters. At this stage, the macro geometry of the wheel is physically fixed. The interplay between the shaft's rotational speed and the optimal water velocity defined the outer radius. With the wheel sized, we shift focus to the volume of fluid required to hit our 1,000 kilowatt power target. Theoretical fluid energy never converts perfectly into mechanical rotation. We must account for the system's overall efficiency, which we have rated at 85. We construct a power equation connecting our efficiency rating, our 380-meter net head, and the specific weight of water, leaving total discharge as our final variable. Solving for discharge reveals that generating 1,000 kilowatts requires a total fluid flow of 0.3155 cubic meters per second. This total flow must be split to accommodate our multi-jet design. Dividing the flow across the system determines the specific discharge per jet, yielding a value of 0.1877 cubic meters per second. We know the volume of water moving per second, and we know its absolute velocity. Dividing flow rate by fluid velocity dictates the exact cross-sectional area required for the nozzle orifice. We translate that area into a secular dimension, locking the internal jet diameter at 0.0487 meters. The engineering model is now complete. The variables are filled, and the machine takes its final physical form.
Following the specific speed constraint from the beginning, we translated our initial targets into a concrete, dimensioned machine optimized for 380 meters of head. However, site conditions are rarely static. When reservoir levels drop during dry seasons, the available head pressure changes. We need to know how this specific machine will perform when its operating environment shifts. To do this, engineers normalize the turbine's performance. They isolate its core hydrodynamic traits from environmental variables by calculating how it would behave under a standardized unit head. This baseline, exactly 1 meter of head, allows for direct comparison between different turbines and different sites. This formula represents unit discharge. It normalizes the fluid flow rate relative to that 1 meter head baseline. The equation shows that flow scales proportionally to the square root of the available head. If the head drops, the discharge follows a predictable square root curve.
Similarly, we use the unit power formula to normalize physical energy output. The relationship here is more extreme. Power output is tied to head raised to the 3/2 power, so a drop in reservoir level causes a disproportionately large loss of output. By distilling complex derived geometries into these unit quantities, engineers create a universal standard. They can accurately predict, scale, and benchmark any turbine's behavior, regardless of shifting site conditions.